we've done a few transnational accesses at UCL, and I'm going to give an overview of two of these. The first of these was implemented a novel rendering technique for immersive virtual reality, and the second one I'm going to talk about implemented an instance of virtually transporting a person from one location to another for meeting and interaction. Well, I would say, just sort of general comments about TNAs. In both these cases, as with all the TNAs, the visiting researchers required access to facilities at UCL that were not available at their own institutions. I mean, this is rather the point of these. So, in a lot of respects, the work of these TNAs starts in the weeks leading up to the visits, so ensuring that the resources they need are available and are working and are configured correctly. The TNA accesses at UCL are for 10 days, so it's important for everyone involved that these 10 days are engaged with the planned research tasks, and that as little time as possible is involved with the resolution of the peripheral technical problems that typically accompany longer-term research projects. So I just got an outline of how I'm going to go through each of these TNAs. I've got a similar structure for each of them. First of all, I'll give a general outline of the proposed research activity, and I'll follow this with a description of the resources at UCL that were required for the research. And after this, I'll provide some background and motivation for this research. So why the visitor wanted to do this research and how the availability of our resources enabled this. After that, I'll describe how the research activities proceeded, and finally, I'll talk about the outcomes of the research and any planned future activities. Okay, so the first of these projects, the visitor was Santiago Martin Gonzalez from the University of Oviedo, and the project was Gaze Contingent Multi-Resolution Graphic Library. The goal of this project was to implement a rendering system that takes account of the user's gaze direction, such that images are rendered in greater detail in the user's gaze direction and with less detail in more peripheral areas. The researcher had been working for some years on the development of a rendering system, but lacked both a wide field of view system on which to implement and test this, and an eye tracking system that would monitor the user's gaze and use this to moderate the rendering algorithm at each frame. So the equipment items that he specifically wanted to use at UCL were our four-wall cave and our eye tracking system. Now our cave, you can see in the picture, has 4 display surfaces. The vertical walls are 3 meters wide by 2.2 meters high, and the floor is 3 by 3 meters. So a user standing in the center of the cave has available a very large field of view, which makes this an ideal system to test the gaze contingent rendering algorithm. Other details, we use InterSense IS900 tracking to track head position and orientation, and this gives us high accuracy and low latency. The eye tracking system we have an Arrington viewpoint tracker, and this uses infrared illumination and cameras pointed towards the eyes to detect and measure corneal reflections. And these same camera images can also be used to detect changes in pupil size with a thresholding algorithm. So the way it works, it takes the images illuminated under infrared light, and it segments the dark pupils and the right corneal reflections. And so I realise I don't have an image of this in my slide, but you can draw a vector from the corneal reflection to the centre of the pupil, and this is used as input to an algorithm that computes gaze direction. The algorithm itself is proprietary to Arrington, but there are a variety, I think, of open algorithms that are probably quite similar available. So you can see in the image below the eye the infrared light, and the camera is pointing in there. There's also an additional outward-facing camera that captures a 2D image of the user's field of view, and you can, once you've computed their gaze path, you can map this onto the image from the outward-facing camera and see exactly what it is they're looking at. An important quality of this particular eye tracker, because we've worked with a number of different ones, is that it's able to work quite effectively on a user wearing LCD shutter glasses and in quite low light, which are the typical conditions in the cave often. Shutter glasses are necessary in the cave for stereo viewing, so any eye tracking system we have has to be able to work through shutter glasses. You can see that we've customized this pair of shutter glasses to mount the viewpoint eye tracker on them so that it can be used in the cave. So the plastic frames of the shutter glasses are augmented by a metal surrounding frame, and this holds the cameras and infrared lights in place, and you can see the outward facing camera mounted above the metal frame between the user's eyes. So the motivation for this research, I'm referring a little bit to the accepted project proposal for this. The background to this research lies in the disjunction between how the human visual system processes visual information and how we typically display visual information with computer graphic systems. So human vision subtends a wide field of view and provides high-resolution detail at the center of gaze with decreasing resolution in the periphery. The fovea comprises less than 1% of the retinal area, but takes up over 50% of the visual cortex in the brain. So the photoreceptor cells in the fovea region are very, very densely packed. There are almost exclusively cones, whereas outside the fovea it's mostly rods. The rod cells function mostly in dim light, and they provide monochrome vision, and they're very sensitive to motion detection, while the cones support color vision and daytime vision. So this characteristic of human vision suggests that ideally most of our computing power should be concentrated to render to the small foveal area, so where you're looking at, whereas the peripheral areas are less important, and we can use more limited computing resources would be sufficient to draw low resolution imagery in the periphery. So this would allow us to decrease or reorient the computational load, especially in a wide field of view system such as the cave. I would say that the software that our visitor was using doesn't do this load balancing yet, but the idea is that we can demonstrate where the load should be with a system like this. Gaze contingent multi-resolution display is the term used for this approach to computer graphics. In addition to the obvious implications for rendering efficiency, this research also has direct application to psychophysical studies of the human visual system, and I think this is something also that our visitor was particularly interested in, and he cites a few examples of these. First of these is saccadic eye movement research. You can see in the picture on the slide, there's a picture of a scene with some people in it, And the three traces, I think, are three traces from, I'm not sure if they're from different people or the same person, but they've been asked different questions about the picture. So they've been asked to say who are the people in the picture, or asked to say what is the relationship between the person who's just come in and everybody else. And other ones, they've been asked to just take a look at the decor of the room, and you can see the different types of traces depending on what people have been drawn to. So saccadic eye movements are very fast eye movements that we use to fixate the phobia on a new area of interest. In other words, we make saccadic eye movements in order to bring new information into the high acuity phobia, and by doing this we build up a visual description of the world around us by constantly looking around and foveating on different parts of a scene. Now there's one quite commonly held theory which assumes that higher level processing of visual information is confined to the phobia, and the processing of peripheral information only plays a role for selecting the next saccade target. I mean, obviously peripheral vision also is used in things like seeing objects that are looming or motion, but the point they're making here is that it's not used for building up a picture of a scene. However, it's hard to demonstrate anything like this experimentally, and the theory remains controversial. So possibly by manipulating the level of detail that we render around the foveal gaze direction, it might be possible to provide experimental evidence that sheds some light on this. Next example is amblyopia, which is sometimes referred to as lazy eye. It's a fairly common condition, and it's something that it happens early in life, and it causes visual processing to become turned off in the visual pathway from one eye to the brain. Not completely turned off, but enough such that one eye becomes very dominant while the other eye provides a more degraded or blurred view of the world. And the consequences of this are poor stereo vision and degraded depth perception. And it's also it's something that's often not picked up. It's often doesn't display obvious symptoms in early childhood, and once beyond early childhood, it's very difficult to fix. So the common way of trying to fix amblyopia is eye patching. You've got to patch over the good eye and force the child to use the less dominant eye more, and build up the visual pathway in that way. Again, there's a controversial theory about amblyopia in this theory is that it's caused by a failure in the dominance of foveal vision compared with peripheral vision. And again, this is something that's not easy to confirm unless you can design tests that use both foveal and extrafoveal stimuli. And obviously, gaze contingent rendering would have an obvious application here. The next example is depth of field simulation. Now, this is, I'm actually going to go over some ground I covered in an earlier Visioneer seminar, because this is somewhere where our visiting researcher and my interests overlapped. There's an ubiquitous problem with all virtual reality displays, is that stereo depth is simulated only for the convergence of the eyes and not for the focus or accommodation. So in other words, we can make an object appear closer by rendering it such that the placement of the left and the right eye views make our eyes converge as if the object were close to us. But we don't affect the focus at all. Now, in the real world, if we look at an object that's close to us, our eyes will converge towards the object so that they both look at the same thing. If you hold your finger in front of your face, you can demonstrate this quite easily. But while this is happening, your eyes will also focus on the close object by adjusting the shape of their lenses. So on the other hand, if you're looking at something that's far away, your eyes will point straight ahead, and the focus will be adjusted to the distant object. So normally, focus or accommodation works in tandem with convergence, and there's a one-to-one mapping between a given focus and a given convergence. So any given convergence angle corresponds to a particular depth, which in turn implies a given focus. It's perfectly possible to elicit focus and conversion outside of this normal mapping, and this is what allows stereopsis to work in practice in all VR displays and in any other 3D display. So the 3D effects are produced entirely by convergence, while the depth at which we focus remains constant, or it remains entirely determined by the distance we are from the display. So if you're standing in a cave, you're constantly going to be focusing at maybe a meter, meter and a half, depending how close you stand to the screens. With a head-mounted display, you're constantly going to be focusing at the distance of the optics, which is typically quite small. A related aspect of this problem is that we typically display all the objects of a virtual scene in sharp focus. This is not the same as our view of the real world. If we look around and foveate, wherever we look, we will tend to focus on. But we realize while we're looking at something, the center of our view allows us to focus on one depth only, with a certain depth of field around that. Gaze contingent displays could be used to simulate depth of field, and it's possible that by doing this we not only improve the display, but we can help mitigate some of the problems of accommodation, convergence conflict, and eye strain from using VR systems. Just one more application, and this is in vestibular disorders and posturography. So the vestibular system is very important for our balance. It's situated in the canal of the ears, and it sends signals to neural mechanisms that control eye movements and muscles that keep us upright and stop us from falling over. So if you have a disorder of the vestibular system, the problem is that you no longer have these automatic signals that are keeping you upright, and you'll maybe compensate a lot with vision when you can, but you will often suffer from vertigo and instability. The interactions among the sensory, motor, and central processing and posture and balance are quite complex, and typical treatment involves an assessment technique called computerized dynamic posturography. And this is carried out, you can see an example in the picture there, by placing the patient in a standing posture on a fixed instrumented platform that's connected to sensitive detectors that detect small wobbles or oscillations of the body as you maintain your balance. You can see there's also a plate in the floor that can be angled to try and tilt them back or forward or place them on a slope. And the imagery you see around them is meant to provide a horizon and some scenery to give them an idea, a visual idea of what way is up in the world. And you can see in this system there's also a small display. Not all posturography systems have video displays in them. The idea of using gaze contingent displays here is that because peripheral vision is more sensitive to motion detection, a gaze contingent display could improve analysis of patient response and give a better or more accurate diagnosis of specific problems. Okay, so the objectives of this TNA visit. The main objective is to implement and test the gaze contingent multi-resolution rendering system in the UCL cave. So although we have these longer term objectives of using a system or building a system to study all these aspects of the human visual system, we considered that realistic objectives for a 2-week project should be focused on the analysis and tuning of the rendering system. Once the software was implemented, the next stage would be to interface the system to the head tracking and eye tracking systems in the cave, and to create a working demonstrator to show different peripheral rendering techniques. So the TNA visit took place during 2 weeks in November 2012. Prior to this, our research visitor had continued the development of the gaze contingent rendering library. The software used was based on the graphic library Stereo Vision engine. This is an open source C# library based on OpenGL using OpenTK as a wrapper, and it supports vertex and fragment shader programming, and is designed primarily to facilitate computer graphics and virtual reality scenarios with detailed control over stereo representations, but without the complex knowledge required to implement all of this just in straight OpenGL. So it sits on top of OpenGL. The GLSV library was developed at the University of Oviedo by our visiting researcher, and it's available in SourceForge if anyone is interested in that. The first problem that we encountered was with porting the software to work on the graphics cluster at UCL. Our researcher had been testing the system on a 2-monitor system at Oviedo, but he was using 2 graphics outputs of a single card, and there had been some assumption that scaling it to work in the cluster would be straightforward, although this didn't prove to be the case. So realizing the impact that this might have on our schedule, we worked simultaneously on a number of potential solutions. Ideally, what we want to do was adapt the library to work in a cluster mode with different processes running in each node to support the different camera views of the same scene. But we realized that if we didn't get this to work, we needed to have some alternative. So we also explored incorporating the library into some of our existing cave software. But we came upon another difficulty doing this, in that what we needed to be able to do with the library was to manipulate rendered images during an additional pass. So we might want to do some selective blurring into the periphery of the image depending on gaze direction. And we found this was incompatible with the structure of any of the network renderers or other software available to us. So in the end, we were able to implement it in clustering mode, and we ran test applications using head tracker orientation to moderate gaze direction. At the same time, we'd also been working on getting the software library to receive data from the eye tracking system. So for this we used VRPN, and specifically a VRPN server class for Arrington research that had already been developed and was available to us. And this software connects to the eye tracker and retrieves gaze position, orientation, and velocity data. However, while we were testing the system, the eye tracking system developed a problem, and in my attempts to fix it, the drivers for the PCI card became corrupted, and the system became completely unusable. At this stage, we were very close to the end of the research visit, and it wasn't possible to repair the system. So the tests we ran of the demonstrator used head tracking only. They briefly had eye tracking, but in the end we ran it with head tracking. So the outcomes of the project, to illustrate the outcomes, we had our working system based on head tracking data. I've also got a short video that I'm going to show you of the software working in the cave. here you just see us shutting out the foreplay, just testing that we've got accurate tracking working, and then we start introducing some effects. Some of these we augmented slightly so they would look better in the video, as you will see, just so we could show the kind of effects we could achieve. And obviously, in a 2-week visit, we were running any extensive user tests, but we were able to demonstrate some simple blurring and masking techniques to demonstrate the system. Since the end of the research visit, we've also been working together on a paper based on our experience of implementing the gaze contingent library in the cave, and we are planning to continue with this line of research. And Santiago Martin, our research visitor, is planning a further short research visit. This is something that's independent of Visionaire, hopefully in the near future, so that we can properly implement the eye tracking in the system, because we were so close to it at the end of last time. And this is with a view to conducting more extensive user studies. The goal of this project was to implement an instance of virtually transporting a person or a visitor from one physical location to another for the purpose of meeting and interaction. So it's a variation in the idea of telepresence, but it's thinking about it more in terms of putting yourself into the other location or having some representation of yourself at the other location. The context of this research was part of a broader research goal at both the visiting institution, the Barcelona's Event Lab, and at UCL. And underlying this broader research goal is the idea of transferring streams of multi-sensory data. This could be visual, audio, haptic, back and forth from one physical place to another, and using this information to create a unified shared space or shared environment that represents the physical space of the destination in real time, which is why we have this concept of a visitor and a destination. And the sensory information of the visitor streamed to the destination as well, so the visitor is going to be represented in any one of a variety of ways. In this instance, the representation was a physical robot, which was something that was quite novel to both of us. The visiting researcher, Xavi Navarro, is based at the Event Lab in Barcelona. His background is in, or the background of the lab is to improve the algorithms and methods and interactive techniques in virtual environments. And his work explored some of the technology and ramifications of the process of transporting people from one physical place in the world to another so they can interact with the local people there. The equipment that they wanted to use at UCL were, well, the cave again, motion capture system. We have 2 motion capture systems at UCL. The plan was to use the 12-camera OptiTrack system, since this gives, as we found, we're able to get coverage of almost the whole volume of the cave using this. And of course, a humanoid robot. Now, this is not a permanent fixture at UCL, but it's something that we had on loan from the manufacturer. It's called Robothespian, and you may have seen this before. There are a number of them around. It's a commercially produced life-size humanoid robot with natural limb movement to the upper body, head, arms, and fingers, and this is achieved with pneumatic electric actuators and a whole array of sensors that monitor its position. As you can see, it also has video-based eyes, which can be programmed to do various things, wink, close, broaden pupil, etc., and also a moving mouth. The motivation for the research. So the goal of the research visit was to achieve a novel mode of link-up between a person trapped in the cave at UCL and another person trapped in an office elsewhere in the same building. So we weren't starting with transport very far, but just across the local network in our building. So the person in the cave would be tracked with a motion capture system, would be the visitor to an office several floors above the cave, and they would see in the cave a model representation of this office inhabited by an avatar of a person trapped in this office. So meanwhile, the person in the office would meet locally with a robot representing the person in the cave. The main technical challenge for our visitor was the implementation and calibration of the human library to transmit live motion capture data to the robot. Human is a software library developed at Event Lab that acts as middleware between motion capture systems and any kind of humanoid entities. Typically was developed for controlling avatars, but in this case it was being used to control a humanoid robot. Tracking in the office of the person there was going to be achieved with a Microsoft Kinect device just mounted at the base of the robot. So it was going to be fairly rough and ready. And once we'd successfully managed a link from the cave to the office, we had a further goal to attempt to link up between UCL and Barcelona. We did have some implementation problems, and we did have to redesign some aspects of the experiment. The main problem was with the tracking in the office. It was just difficult to achieve good quality tracking with Kinect. We tried this before successfully many times, but I'm not sure if it was just the environment or the light or what it was, but while we thought that the gross tracking measure from the Kinect would be sufficient, it just seemed to work particularly badly in this setting. So an obvious alternative was to instead use the video feed from the robot. So this would obviate the need for any tracking. The thespian robot has stereo cameras mounted on the robot's head and can provide a real-time 3D stereo video stream. So this seems like a great solution, but is not without problem itself. If you use the video feed, then you have implications for the setup in the cave, because a video feed is not an ideal data feed for a cave environment. It can't be used in conjunction with modeled environment because the video has both the person and the real environment in it. And also stereo video really requires a static viewpoint for the person in the cave. The robot, although it can move its head and its arms, it can't walk about like a person in the cave normally can. An additional and more ambitious component of the project was to attempt a link-up between UCL and the Event Lab in Barcelona. And this could proceed without the same degree of design compromise because there was a completely different hardware setup at the Event Lab. So here the visitor used an XN's MBN motion capture suit, and they also wore NVIS111 head-mounted display to experience the stereo video and audio feed from UCL. So the XN's motion capture suit's a Lycra suit with built-in inertial sensors, and the data from these sensors was propagated via the human middleware and transmitted to UCL to control the robot in an office there. You can see in the picture. Video is streamed using software developed at the event lab, and for the audio we just use Skype. The stereo video works okay with HMD. You still have these limits in terms of tracking, but in terms of visual feed it works much better there than it would in a cave system. So outcomes. Other than the Connect tracking, the overall system worked very well, and the link up between UCL and Event Lab generated quite a bit of media attention in both countries. Both the BBC, British Broadcasting Corporation, and Catalan television station Y3S covered the event, and I'm going to show a short clip of the BBC coverage.
So we've come to University College London for a bit of a meeting about technology called beaming. We're meeting Professor Mel Slater here. You're heavily involved in the project. Right, yes. And also joining us is Dr. Mavi Sanchez-Pibes. Good morning, Mavi.
Good morning.
Nice to see you. Nice to see you. So, Mel, what's all this about?
This project called beaming allows someone to instantaneously transport themselves physically to another location. So Mavi here is in Barcelona. Hello, Mavi. And she's joined us and she's embodied through this robot. So there's a lot of technology going on here across the internet. Her body is tracked. The movements are translated to the movements of the robot. When she speaks, you hear her speak, and she can see us in full 3D stereo from the eyes of the robot.
So Mavi, let me get this straight. You're not here, you're in Barcelona.
Yes, I'm in Barcelona.
You seem to me to be in London.
Well, in a way I'm in London.
What's it like at your end?
I'm in a lab. It's similar to the one where you are, or in a room where there is some equipment around and also a camera, although I cannot see it because I'm very head-mounted display, and actually the environment in which I can see is the one where you are in London.
So you can see me, you're looking at me now.
Yes, I can see you. Also, I can see my hands when I lift them, and then I can look around. So when I move around, I can see the room and the walls and everybody there. I could say I'm there in a way.
Should we do a high five?
All right.
Thanks, Mavi. Good meeting you.
Okay, so that actually concludes both the presentations.
You investigate a solution to get an avatar which is represented by a robot. Did you test it over kind of avatars? Because, for example, right now I can see Dovdori as a 2D video avatar. And a classical on a classical display. Would you have some example of indicators that could be used to compare the two situations? And maybe we could have some intermediary systems to have other avatars and to be able to compare the quality of the avatar. Did you thought about that?
I think that there's quite a lot of work in this area that I can't cite off the top of my head, but the idea behind this kind of work, or the premise behind it, is to get something that is better than video conferencing systems, because video conferencing systems have been around in time, but people still don't use them. So you ask the question, well, why do people still fly across the Atlantic to go to a meeting, why don't they just use video conferencing that would be cheaper and would take less time and would be better for the environment, yet people still want to have the physical meeting. And the answer is that things like video conferencing are still very limited. They don't carry the subtle social cues that happen in a normal meeting. I'm sure you've been in conferences before, or even a situation like we have right now, where it's difficult to maintain a conversation with lots of people, and where you have the normal turn-taking cues that occur in normal conversations. I mean, I'm aware, even as I answer this question, that I'm maybe giving longer answers than I would in a normal meeting. There would probably be more turn-taking happening and people jumping in and saying something if we were all sitting in a room together, rather than doing this across a link like we have at the moment. So how can you introduce these cues? And one way to do that is through these kinds of technologies that take account of the position, that provide a representation of you that is going to look at the other person in the appropriate direction and is going to turn, and you see people in the appropriate physical locations rather than just on a panel on a video screen. Was that what you were asking?
Yeah, it was the main question. I was wondering also if the speed of the robot was a constraint for the person in Barcelona. Was she supposed to go slowly in order to respect the speed of the robot? Maybe a problem for the robot to follow the movement. Was it?
Sure. I mean, this is always a problem in robotics, and having actuators that are responsive, but also at the same time that you have health and safety considerations, because if you're looking at a video feed, you might not you might not have the vision to realize that you're about to hit somebody with your arm if you move too quickly. The robot that we used has a very nice movement. It uses pneumatic and electric actuators, so it gives a very natural, very natural looking movement. One of the big difficulties, and this is something that Xavi spent a long time with, was just getting the system calibrated well so that the movements of the person being tracked, either by the motion capture system at UCL or the motion capture suite in Barcelona, so that any movements or arm gestures were faithfully represented by the robot. And I think that took quite a bit of doing.
I was wondering on this subject, what was the model for multi-resolution you used? Did you have multi-resolution of the graphic scene by itself of the objects? What kind of system did you use for that? Or was it just a cutting plane model? Everything which is out of a cone is not displayed. I did not clearly understand that.
What we would do is, based on the gaze direction, you manipulate the level of detail in the periphery, and you can do this in a variety of different ways. You might remove the color from it, for example, because our peripheral vision is largely monochrome. There are very few cone cells involved. So you might make it monochrome, you might just reduce the level of detail. Now, what Santiago's system does is simulate all these effects. So it takes a normal rendered image and then does a kind of second pass over it, which might pass a Gaussian filter to blur it, or something that removes the color at a certain distance from the gaze point. But ultimately, this is not what you want to do, because this is actually going to take more processing power, not less processing power, which is one of the goals of this. But the idea is that by testing this system and seeing how well it performs, you can think about designing rendering algorithms that actually don't do a lot of this processing in the first place. Now, obviously, this is would be a very difficult thing to do, and there are, I suppose, broadly two ways of going about this. If you want to think about decreasing level of detail or blurring more in the periphery, one would be to just render a lower resolution in the periphery, and the other would be to use different models in your scene, or use lower resolution models if they are further out of the cone of vision.
Okay, and to get that, you were expecting to use the eye tracking. As I understood, it was not working by the hand of the process because there was a problem in the software.
Yeah, this was unfortunate, and we still haven't actually repaired it yet. But Santiago Martin has contacted me recently, and he wants to come back and try it with the eye tracker. So we're going to try and get that fixed again. It's a software issue. Well, we don't think it's a hardware issue. So it should be something that we can do.
My comment was, I had two comments. First, it will be a second transnational access project if you expect to go further in this direction, since it has not been enough with the first project to do it. So it will go towards a second transnational access project. This is
it's something we'll certainly think about, and I think it's something I'll talk to him about. But at the moment, the getting the eye tracker ready will be something that will be very short, and I think he's managing to get some funding from his institution to come and do this visit. But yeah, further on, we might try for another transnational access visit and do more extensive testing.
So we can upgrade the subject in order to get more impact and more feedback, I guess. But also, I was just answering myself what was the weight of the shutter glasses with the tracking system, the eye tracking system, in order to know the weight for a head.
It's actually okay. It's not bad. I mean, you do have to, the shutter glasses, we've actually taken the arms off the shutter glasses. It's maybe not obvious from the picture I showed, and use an elastic strap to hold them in place. But it's not too heavy. You don't have to have it really tight, and you don't end up with marks all over your face after you've finished using it. So it's quite a lightweight design. As long as you balance the cables that come from the eye tracker over your shoulder, then it's fine.
Okay, it's not like a head-mounted device or something like that.
No, it's nothing like that.